Physics is exceptionally good at predicting smooth, continuous movements, like the sweeping arcs of orbital mechanics. But classical equations struggle when forced to confront violent, instantaneous physical collisions. Standard applications of force equaling mass times acceleration assume forces that can be reliably tracked over a period of time. An impact event is chaotic, defined by rapid, unpredictable spikes in force that standard acceleration metrics simply cannot model. To solve these impact events, we cannot rely on standard acceleration calculations. We have to rederive Newton's second law from the ground up. Understanding these interactions requires us to shift our focus entirely. Instead of acceleration, we must track the transfer of mass and velocity as a single unit, a vector quantity known as linear momentum. Newton's second law states force equals mass times acceleration. Expanding acceleration, we rewrite this as mass times the derivative of velocity. In classical mechanics, mass is constant, so we pull the mass variable inside the derivative function. This isolated term, mass times velocity, is defined as linear momentum, p. Substituting this back establishes a new rule. Force is the rate of change of momentum. Because velocity dictates direction, momentum adopts that exact sign as a vector quantity. Force functions as an active agent of momentum transfer over time, representing a dynamic shift from the static pushes and pulls of basic kinematics. This diagram illustrates a system boundary. When an external force acts across this boundary, physicists state that it delivers an impulse. Because the actual forces of a collision fluctuate wildly, we isolate the event by integrating the force over the precise time interval of the crash. The result of this integral equals the total change in momentum. This schematic demonstrates a real-world application, determining average force on a car rebounding off a wall. Because momentum is a vector quantity, a rebound requires mathematically accounting for opposite directional signs: negative for initial approach, positive for departure. Looking at this step-by-step solution, we see that stopping the car and reversing its direction resulted in a total momentum change of 8,100 kilogram-meters per second. This required an average force of 54,000 newtons from the wall. The impulse integral is a vital tool. It allows us to bypass the unmeasurable, chaotic force spikes of the crash entirely, calculating exact limits using solely the boundary conditions of the initial and final states. We can alter the math entirely if we expand our perspective. We simply draw our system boundary large enough to enclose both interacting objects in a collision. In this diagram of two interacting particles, expanding the boundary means there are no outside forces crossing into the system. The violent forces of the collision are now entirely internal. Newton's third law dictates that these internal impact forces perfectly cancel each other out. The mathematical consequence is absolute. If the net force is zero, the time derivative of the total combined momentum of the system must also be exactly zero. This establishes the universal invariant of isolated systems. Regardless of internal chaos during impact, the total momentum of a closed system is constant. The initial vector sum perfectly equals the final vector sum. Because momentum is conserved in every isolated interaction, regardless of whether objects bounce or break, it cannot distinguish between different collision types. To classify these events, physicists must introduce a second metric, kinetic energy. An elastic collision is an event where particles rebound with absolute perfection, and zero kinetic energy is lost. These occur almost exclusively at the theoretical or microscopic level. Macroscopic, real-world events are inelastic collisions. Here, kinetic energy is permanently lost, converting into heat, sound, or structural deformation of the materials. Yet, regardless of the kinetic energy destroyed, whether objects bounce flawlessly or crumple violently, the total linear momentum of the system remains absolute. Calculating the outcome of physical impacts depends on the strategic placement of the system boundary, which renders the chaotic internal forces irrelevant to the final solution.